Okay, so for problem 2, we have to calculate the infinitesimal potential along the x-axis due to the ring. And we are told to take the potential at infinity to be 0. So we use the same geometry as problem 1. We have that here. And we know that the infinitesimally small charge Q equals the charge density times an infinitesimally small area. So what is the area? If we look over here, the area of a disk is pi r squared. And if we want to differentiate with respect to r, we will get 2 pi r, and we move the dr over to the right-hand side, which would give us 2 pi r dr. Now we have our dA. We plug it in here. dq equals the charge density times 2 pi r dr. So we also know that an infinitesimally small potential equals the constant k times an infinitesimally small charge divided by the distance. Now the distance for this disk would be r, the point from where r meets the inner disk, to x. And what is the length of d? D is simply a Pythagorean theorem. X squared plus r squared will equal d squared. So when we plug in dv equals k dv, and d is the square root of x squared plus r squared. Now we have our dq, and we plug in dq from here. We'll just draw a little arrow, and we plug in to give us dv equals k sigma 2 pi r dr divided by the square root of x squared plus r squared. And this is our answer to A. Okay, so in order to make this a little bit neater, let me move this in here. Now, we have B, and B asks us to calculate the potential V along the x-axis due to the entire disk. So we already have our equation. All we need to do is take the integral. So we take the integral of this equation, and we will move all the constants over to the left of the integral sign, and that'll give us k sigma 2 pi, and let us not forget our limits, which will be from 0 to r, and we're integrating this equation here. So using u substitution, we will get that this equation becomes okay, so let us plug in r. So if we plug in for 0, what we get on the right hand side is, hold on, let me first plug in r, I guess. So let's plug in r. That will give us the integral of x squared plus big R squared. And on the right hand side, on the other limit, we're going to get 0. So it's going to be the square root of x squared, which will give us simply x. or the absolute value of x actually. And let us not forget one more bracket. And this is our answer for part B. So, part C. What is the potential in limit when x over r is much less than 1? So let's look at that. When x over r is much less than, when x is much less than r, we can take it as x being 0. When we plug it into this equation, it becomes now remember, x is 0, so the square root of r squared will be the absolute value of r. And x again is 0 here, so it's minus 0. So we have, okay, so now that we have this, we can substitute sigma. What is sigma? Sigma is simply Q over area. So let's plug that in. It'll be K, Q, the rest is the same, divided by the area. What is the area of the disk? 2 pi, no, sorry, pi r squared. We can cancel some terms out and get, or actually, let's see. We can cancel the pi and we'll get 2. We'll cancel 1r. And rewriting it, we should get 2q over r. And that is answer to the C. So the second part to C asks, is this result expected? And yes, this is expected. This is actually the potential at the center of the disk. Since x is 0, x is all the way here. It's basically the potential at the center of the disk. Well, we have D now. What is the potential in the limit when r divided by x is much less than 1? Is the result expected? So the first part of D, we'll look at this equation again, and we'll distribute x squared from this entire part of the equation. So it becomes V equals K sigma 2 pi. Now since we're dividing by x squared across this whole thing, this the square root of x squared becomes x times 1, because we're dividing by x squared inside the square root, plus r squared divided by x squared. Now the square root of x squared is x, so we're dividing this part also by x, which will equal a 1. Now when r divided by x is much less than 1, we can approximate this. It's approximate, which allows us to remove the square root sign. And this equation becomes V equals K sigma 2 pi x 1 plus r squared divided by x squared minus 1. Now in here we have 1 minus 1. So this becomes, okay, sigma 2 pi x. This 1 cancels out with this 1 like this. And since the ratio r over x is much less than 1, we can take it as if r. Okay, so hold on. I want to make this a little bit more clear. Okay, so we have this so far. Let me rewrite the whole thing That way it's very clear. It's going to be k sigma 2 pi x r squared divided by x squared. Now remember, sigma equals q divided by pi r squared. So let's just plug that in. It's going to be q 2 pi x r squared divided by pi r squared x squared. Here we can cancel many things. We have the r squared that cancels. One of the x's cancels. Pi cancels. Okay, so I canceled out many things, but I just noticed that by binomial expansion, this should actually be 1/2. Now, if you don't know binomial expansion, you could always Google it. So let me bring over this 1/2 over here also. And let me put it here as well. So it's going to be 1/2. Now, this helps the 2 in the numerator cancel out with the 2 in the denominator. Now, our final answer will be kq divided by r. This is our answer for D, and this is expected, as the question asks. Is this result expected? Yes, because this is the potential of a point charge with a value q.
I'm going to solve answer E, okay? And answer question E says, use your result from part B to find expression of EX and compare it to your result from problem 1. And is this expected? So from B we have V is equal to 2k0 pi r square x square plus r square minus x root. And what we know is that we know E is equal to dv by dx, and now E is dv. We know that k sigma 2 pi minus x square plus r square. Yes, then here sigma is equal to q0 pi r square and k is equal to 1 by 4 pi sigma square. E is equal to k sigma 2 pi minus x square plus r square is the answer.